Hello, so today we are going to do this problem, best team with no conflict, which is part of Leetcode Daily Challenge. So we have, basically we are a manager of a basketball team, and for tournaments we want to choose the team with the highest overall score. And the definition of a score of a team is basically the sum of the scores of each player in that team, such that there is no conflict, right? And what they mean by conflict is that if a younger player, right, so there are one younger player, one older player, if the younger player has a strictly higher score than an older player, then there is a conflict, right? So basically, the younger you are, the lower your score needs to be. If it's bigger than another older a player in the same team, then there is a conflict. Okay, so that's what the problem tells us. And ages here is just the ages of the players, and scores is the score of the players. Okay, and so we can construct a team with as many elements as we want, as many players as we want, as long as we maintain the condition that there is no conflict and it has the highest overall score, right? So that's pretty much it for the problem. For example, for the first example, it's better to take the entire thing because there is no conflict. If you look at the scores here, they are increasing order in terms of the ages, right? If for the second example, it's better to choose these last three, right? Because then these two are equal, but they do have the same age, so that's fine. And then for these two, this one is younger, it has the smaller score. For these two, since this one is younger, it has this one actually is younger. This one, it has a smaller score of 5, smaller than 6, right? So it makes sense to take. If you take 4, then for example, let's say you take 4 and just taking these two, right? The age, the first one is older, right? Because the age is 2. But the second one has a higher score, right? So it violates the condition. There is a conflict. So that's why we can't take this 4 here. So that's the idea, basically. Okay, so how do we solve this? So the idea is actually similar to LAS, which in dynamic programming is longest increasing subsequence, where basically you have you have an array and you want to find the longest subsequence that is increasing. So it's 1, 2, 3, 4, 5, something like that, or 6, 8, 12. So that's maybe it's in between some other values, right? So we want to find the subsequence, right? In this case, it's actually the same, except instead of, we still want to find a subsequence, right? That's the highest overall score. We still want to find the total, the subsequence, and we still want increasing, but the definition here is a little bit different. So for us, it's sort of not increasing, but without conflict. Increasing without a conflict. And increasing for us means basically in terms of age, right? Without conflict. And then the longest for us here is just the highest total sum instead of length. Okay, total score. But otherwise, the structure is very similar, okay? And so how do we solve it? Well, the idea is that when you are at an I position, right, in terms of like, if you sort by age, so remember what we want is younger player. So for a younger player, and then you have an older player, right? If you take the score of the younger one, should be always smaller or equal to the score of the older one. That's basically the definition of no conflict in a team, right? And so let's define J as to be the index for the younger one and I to be the index of the older one. Just define it like this, okay? And so what this means basically is that we need scores for the younger one to be smaller or equal to the scores for the older one, which is I, right? But here I just suppose these are the indices, but how do we make sure that this one is younger than this one? Well, let's just sort the age and then traverse the sorted list, right? So that's the idea. So sort age, and then basically do I for basically from 0 to n in this sorted list, right? So that we fix the ages in sorted order, and now we just need to find the possible subsequences that have this property, no conflict, and then we pick the highest one. So it becomes straightforward from there. So in that case, how do we do it? Well, you know the longest increasing subsequence is already uses dp, right? And so what we can define is we can define dp of I as the longest, so basically the highest score, let's call it total score because it's going to be a sum, okay, without conflict of teams, without conflict, and then ending at I. And so to look at I, we just need to look at all j's, and then so for all j in 0 to n to I, of course, right? Because we want to look at the previous ones because those are the ones where we are guaranteed that they are younger, right? For the other ones, we don't want to look at them because we are not guaranteed that it's because the beyond I, right? J would be older than I, and that's different than what we assumed here. And we want to do for this property, right? And so to do this here, then we will need this to be just dp of I in terms of j is going to be just the max of dp of I, okay? And then what should be the relation here? We know we need to add the score for which position. We need to add the score for I, right? But we also want to know what's the highest total score without conflict ending at j, and then we are just adding a on top of it. So you can think of this basically as we have something like this, and we have I here. And we know we want to calculate with this I value, but we don't know which subsequence before I works well with I, right? And which one will give us the highest value. And so we try this one, we try this one, we try this one. And by try, I mean basically it means reapplying the same logic for the subarray ending at j. Maybe we take all of them, and maybe we take only a subsequence, right? And so this would mean here that it's exactly dp of j, because that's exactly what we are doing. We just try different j values and then just add to that j the value at I, and that's what we are doing here, okay? But the other constraint is for each dp of I, we need to maintain that there is no conflict. And we suppose that this j here, dp of j, did maintain that. But how do we check? Well, we just said that we need to check using this formula here. We already know that the ages are sorted and this j is younger and I is older. And so we can just use this formula that we have here, right? Score of j needs to be smaller or equal to the scores of I. Okay, so that's exactly what we are going to do here. So this would be if score of j is smaller or equal to score of I. Okay, and that's pretty much it. And now to apply this into an example, let's actually try to run it on let's try to run it on this one here. So we have score and we get an age, and the score is 4, 5, 6, 5, and the ages are 2, 1, 2, 1. Okay, so let's run it on this example. So if we want to sort, so first we want to sort by age, and let's put them in a sort of pair, right? So score, let's actually put them in a pair of age score. So that would be basically something like, well, age is first 2, 4, and then age is first 1, 5, and then 2, 6, and then 1, 5. And then we sort them, right? And so we want to sort them, so we get sorted age score. Let's call these maybe players because we are creating a team, right? And so if we sort this, then we'll get 1, 5, So by the way, we are sorting by what? We are sorting by age first, because that's where we are going to loop on and assume that the fir- the smallest indices ones are younger than the next one. And so here, this would mean we are sorting by age, so by the first value, and then only if they are equal do we sort by the second value. Here they are equal already, so that's fine. And then what is the next smallest? Well, the next smallest is just, there is 2, 4, and 2, 6. The ages are equal, so we check using the score. So 2, 4 is smaller, and then we have 2, 6. Okay, so now that we sorted, we can just go through for each I. So I starts out at here, and so we'll create our DP, right? And so our DP array here will start first with just 0 values. But we know that, well, for each I, we definitely want to initialize it to the base case, which is just the score at I, because you will need to include the elements itself, and then what I said here, look for a possible j that you can add to it. Okay? And so to do that, and maybe you don't find any solution, or even the best solution may be just taking this one alone, and so we want to take that into account. So that's why initially here we will initialize 2 scores of at I. So that's what we do here. So we initialize 2 scores of I, which is 5. Okay, sorry about that. And so we initialize to 5 here, and then we move our I pointer to the next entry, so our I pointer here, and so we start moving j. So j starts out from the beginning, right? So we said j goes from 0 to I, which means basically this is open interval, so basically not including I. That's what I mean by that. And so we have 5, and so we check, is 5 smaller or equal to 5? Yes. And so we add them together using this piece of the formula here. 10, is 10 bigger than 5? Yes, so we replace by 10 here. Sorry, this is for the slot at I. So this means we replace by 10 here, okay? And then now j is done because it reached I, and so we move I again, so I becomes here. And now we check, for j's we start out here first, and we compare the scores. So 5, is 5 smaller or equal to 4? No, right? And so this immediately tells us that there is a conflict, and so we should skip. And so we advance j, and now we have the same problem because it's 5. So we advance j again, we reach I, so we are done. And then we move I here, okay? And so we move I here, we do j. What about 5 and 6 in this case? Well, then it's valid, right? And so, so we are here, by the way. And by the way, here, as I said, we initialize with the score of the value itself. But for this one, well, we initialize first to 6, but then we compare 6 to get the max between 6 and, what is the other alternative? Well, the other alternative is dp of j, which means dp of this one, which is 5. So it's 5 plus the score, which is 6, so it's 11. So it's better to put 11 here. And then we try j, advancing j here, we get the same outcome, so it stays the same. We advance j here, we get, well, what do we get? dp of j, which is 4. So we get 4 plus, plus the score, right? So plus 6, so we get 10. 11 is, the max between 11 and 10 is 11, so we put 11, and pretty much. So for 1j here, I forgot to add for the value of this 5 here, and so it becomes 16, okay? And so that's the result that we return. We return the max. At the end, we just need to return the max because that's the highest value. And that's pretty much it. That's pretty much the idea. So sorting, that way you fix age, and we just have to deal with making sure the scores are do not have conflict. And then with the dynamic programming approach, for each I, we calculate what's before, and that's pretty much it. In terms of time complexity, this is going to be 2 loops because we are going to do 1 loop for I values and 1 loop for j values, right? And so overall, this is going to be roughly open squarish because here we don't go through all the list every time, but still in terms of time complexity, it's open squared. In terms of space, we are using only this dp array, so it's O of n, right? because that's the max we can add to this DP. Yeah, so that's pretty much it. Now let's solve it and make sure it passes test cases. Okay, so let's implement this solution. So first what we need to do is basically just sort a zip of the ages and scores. So this will end up sorting by the first entry, so it will end up sorting by age. And so let's call this A, right? And then we need to just an easier way to access the scores, because in the solution you see we compare them every time, right? So I'll just say sorted scores because it's after we sorted. It's going to be just equal to A, right? It's position 1 because it's the second pair so this is going to be, let's say, X for X in A. Okay, or yeah, something like that. And now we just need N to keep track of the length. So let's just call it the length of the scores. And then what we need to do is our DP array, which is going to be 0 for each place. And now we need to go through for I, and for each I, as we said, we need to initialize it with this is going to be sorted scores, of course, of I. And then we go through J's. It's going to be for the range in I. And now we need to do max of DP of J, DP of I. And it's going to be DP of I is equal to this. And then it's starting from J to the end, so the DP of that, plus the value for I, which is sorted scores at I. And the other thing we need to make sure here is no conflict. And so how do we check that? We just check that we know already that the J is younger than I. So to have the condition of non-conflict be valid, we just need the scores of the younger one to be smaller than the scores of the older one. Okay, so this means the scores of the younger one, which is J, needs to be, and of course we want to use sorted scores because those are the sorted values, is smaller or equal to the sorted scores for I, right? And if that's the case, then we should be able to do this. We should be able to take it. If not, we can't because there is a conflict. And then at the end, we want to return the max of them overall. So the max of DP. And looks like this needs to be N, of course. Looks good. And it passes test cases. Yeah. Yeah, so that's pretty much it for this problem. More, I think, on the difficult medium side than usual medium problems. Yeah, but that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.